Assalamualaikum. We will be covering the other two sets of relaxation oscillators today, which are we covered the triangular waveform generating relaxation oscillator, but today we will be covering the one which will produce a square waveform and a sawtooth waveform, right? So let's move toward that specified oscillator. Now this is the circuit of your sawtooth waveform generating oscillator. It's a voltage control VCO oscillator, right? And the devices used, now this is the same familiar circuit of your integrator with a resistor and a capacitor, right? The new element is this UJT, unijunction transistor, which is controlled with the help of a voltage, and an input voltage, DC voltage, is applied, right? So what's a unijunction transistor? Now your UJT is somewhat like this, right? It's consisting of a P and a N, but P element is very small, right? So it produces a kind of resistive effect and in between this path, right? And two resistance elements are when you draw an equivalent electrical equivalent circuit. So it's somewhat like this, right? And because there is a P and an N state here, so there is a diode element here, right? So what happens that it's normally off unless and until you apply a voltage which is approximately 0.7 here, because when no specified voltage is applied on your emitter, this diode is in off state, right? And similarly जो आपकी emitter जो आपका terminal होगा, this would also be non-conducting, right? So UJT is switched off, right? And zero current flows through it. And when you apply a voltage here, right, so it produces the equivalent voltages VRB1 and VRB2 and etc. VBB, right? And VBB is the voltage applied across it, right? So when this scenario is achieved and you apply a 0.7 volt, in that case current flow through this specified region and your UJT is conducting. I'm not going into the deeper details of UJT. I'm just giving you the minor concept. If you want to go into the details, you can write about it, right? So anyhow, now when you are actually applying this UJT in this circuit, so what happens here that you are normally turning your emitter to on state, right? But there's an anode and cathode element here as well, right? And your diode is normally in off state, right? Because your voltage V output जो है यहाँ से जो आप feedback करें, it's this diode is totally dependent upon this output voltage. So normally when a voltage is applied here and this is your integrator circuit, it will produce a triangular waveform as an output, right? And your capacitor would be charging in that specific scenario. It's in turn off state at that time, right? आपका करंट यहाँ से फ्लो हो रहा होगा, right? This path, from this path it's in off state, right? And your waveform would be somewhat like this, right? Unless and until your output voltage reaches to a point that your diode is triggered on, right? Means your output voltage is up to 0.7, right? So at that stage when your diode is triggered on, या circuit आपका on हो जाता है, your capacitor starts to discharge via the circuit. So your V out suddenly drops because of this discharge current. Your output voltage is suddenly dropped, right? So this dropping elements produce that sawtooth waveform, right? Start में triangular जा रही थी, then because of the discharging of the capacitor via your diode path, sudden drop comes in your V out, and that drop is indicated with the help of line. Now again the RC time constant counts here, and your discharging can vary, and accordingly आपकी sawtooth wave भी vary कर सकती है if you change your capacitor value as well, right? So your unijunction transistor is basically consisting of an anode and cathode and a gate terminal, right? Now your gate terminal is continuously positively biased, right? You have applied a voltage to it, so it's normally on, right? It's positive with respect to your cathode. So when you apply, or when your voltage of cathode exceeds the value of your gate voltage, let's say roughly 0.7 volts, then your unijunction transistor is turned on, right? At that time it's forward biased, right? And your device is turned on and your capacitor discharged via that path and आपका जो sudden drop आएगा that will be created with the help of this scenario, right? So how you can calculate the voltage, the frequency, your time constant? It has specified formula. Now your sawtooth amplitude and period can be adjusted by your unijunction transistor gate voltage, right? If you vary your gate voltage, you can also change the amplitude and period of your sawtooth wave, right? And also it is dependent on your RC time constant. Now your time period of your specified wave is actually the difference of the VP and VF. Your VP voltage is actually the voltage which is occurring when this is the voltage which you are applying on your gate, right? So let's say if you are applying 5 volts, 10 volts, whatever, right? So up to the maximum peak which is going in the triangular waveform, right? That is your VP, right? And VF is जब आपका drop आता है in your voltage and suddenly that drops goes, it can be either up to 0 or sometimes it's a bit more than 0, right? So you can use roughly an estimated value of 0.5, 1 or 0, right, for VF, and VP will be with the help of your specified whatever source you are using, right? So when you calculate the time constant, it is dependent upon your VP, VF, Vin. Again, Vin is the applied voltage which is in inverted direction and it's applied to your integrator circuit, right? And finally the final required element is your R and C. So with the help of these set of devices R, C, Vin, VP and VF, we can calculate the frequency and we can produce a sawtooth waveform. So you will be using in all of these 3 set of experiments, you will be observing this frequency with the help of your oscilloscope and you will be calculating it with the help of all the given values, right? So the final oscillator is your the oscillator which will be producing your triangular waveform, sorry, square waveform, right? So it's a square wave oscillator. Now this oscillator is comprising of a differentiator. This is the circuit of a differentiator, capacitor in the input path and a feedback loop consist of a resistor, right? And this side is somewhat similar to your comparator. You are taking the output and feeding it back with the help of a wide voltage divider circuit. So flipping between your positive and negative voltage will be produced with the help of your this comparator circuit element, right? And differentiator will be used to produce a constant voltage level, right? So if you want to go into the details of differentiator, you know that a current is flowing from here to output. So input current is equal to your I forward loop current, which is equivalent to the output divided by R of F, right? So you know that input current is equal to, it's a capacitor in the input part, so C times dV in by dt, right? But it's also equivalent to IF. So put this value minus V out divided by RF is equal to C times dV in divided by dt. So you produce a V out is equivalent to RF times differentiation of your input voltage, right? So this is exactly used here in the negative loop. You are using your differentiator circuit, right? Similar negative loop differentiator circuit. So when you are actually using this circuit, now your non-inverting circuit has a 2 set of resistors, right, in the feedback loop, right? Now these are actually feeding back the output voltage in the form of your voltage divider, and it's somewhat similar to what we did in your initial circuit of comparator here, right? If you remember what we did in the comparator, we took the output voltage and we fed it back to the positive loop with the help of a voltage divider. And what does a comparator do? ये आप flip करता है आपके positive और negative voltage levels में, and there's a reference voltage and there is a negative voltage required, right? So this is your V input is actually what I'm feeding back from my V output, right? And your reference voltage I have set here is actually grounded, right? ये आपकी reference voltage है, right? And you are feeding it back to the input. So if this fed voltage in your present case, if it's now this is your fed back voltage, if it's greater than your reference voltage, it would be a positive output, right? If it's less than your reference voltage, it would be a negative output. That's how your comparator parts work. So when you combine these two parts, somehow what happens, initially there's no voltage here, right? When there's no voltage here, आपकी यहाँ पे भी ज़ीरो होगा, यहाँ पे भी ज़ीरो होगा, but because it's an oscillator, so minor output voltage would be again fed back. So whatever is the voltage here would be the voltage here. Vf would be also appearing on your this terminal, and capacitor would be charged for this specified Vf voltage, right? So initially your capacitor voltage would be somehow a rising curve, and up to the point it is charged to the maximum value of Vf, right? Whatever voltage is appearing here is charging up your capacitor. Now up to that specific point when it's completely charged, वहाँ पे जाके your comparator will flip your output voltage, right? Because you have a maximum voltage here and your comparator terminal is your जो आपकी reference है, that is increased from your input voltage of comparator, right? So your output would be flipped, right? So as soon as your output is flipped, if you draw a line here, it will start to discharge up to 0, right? And again, because now your negative voltage is being fed back to your input, so capacitor will then charge to a maximum value of negative voltage, right? फिर ये charge होगा up to maximum of negative, right? Then again आपकी voltage flip हो जाएगी, then it will discharge and charge up to a maximum of positive, discharge and charge up to a maximum of negative. So because this is your input terminal waveform, right? When you apply it to a differentiator, let's say it's a T, and you apply d by dt to that T, so what will happen? A constant amplitude, constant amplitude, right? So this is how you're generating your square waveform oscillator, right? So these are the three sets of relaxation oscillators which you would be covering in your lab. So this is all for your theory part.